Okay, can you guys hear me? Okay, sounds good. So you guys survived the third day, almost done. So hope you guys learned a lot and enjoying this workshop. Actually, I will have 1 hour. I kind of divided between explosive electron emission and talking about a little bit about vacuum diode. You guys probably have heard a lot of these concepts in a slightly different context, because when you talk about conventional microwave devices, usually we are describing electron beams, electrons with the relatively lower current regime. In this context, we are talking about in high power microwaves, it's basically kiloamps of current, tens of kiloamps of current. So there's a lot of charge in the system. Fermionic emission that you guys learned about today and yesterday, Kashif and Ayub and other scientists described to you.
But just kiloamps current, isn't it?
Yes, yes.
Not a continuous rate.
It's pulsed, yeah.
Pulsed.
So there's 2 things that prevent us from having continuous or DC. One, you don't have a DC power supply can support that. Second, there is no need for the application, such application. The application and the cost always restrict you as an engineer or a scientist, because you don't want to just invent something nobody will use, right? So you want to have application in your mind, then cost, you want to have a reasonable cost. You don't want to have a machine with the multi-billion-dollar and then the effect or the use is basically so limited. So all of these are going to contribute to your decision. So in order to put you in context, let me go ahead and talk about the block diagram. So I'll start with this, and then I will hide behind this table and use the tablet a little bit. So the block diagram you see here, it's basically for any vacuum electron device or like high power microwave tubes, except that in our context, usually we are trying to have electron gun concept is combined with the microwave source. Everything is one device. And this is because you don't want to have multiple electrodes. You saw this morning, to design an electron gun, you need to have some ceramic and then another electrode, focusing electrode. You don't want to have all of this because you are talking about kiloamps of current. That's a lot of current. And whenever you have small gaps, you end up with the arcing. So you're not going to be using the electron gun efficiently. Fermionic emission cannot support or give you that range of current. I will show you next table. Now, in this table, on this graph here, you will see the conventional microwave devices. Usually, they can push it to have subrelativistic energies, MEVs, but the current is relatively smaller, you know, and that these sources will have impedance, high impedance sources, basically. High power microwave are relatively lower side of the plot here. So here is our high power microwave devices. We are talking about 100 to a couple of hundreds of ohms, all the way to low single digit impedance. And the reason why, because the current is high. Of course, impedance is going to be voltage. If you are talking about hundreds of kilovolt and tens of kiloamps, you're going to have a lower impedance. The ratio is going to be lower. Okay, so this is just to give you a perspective what we are trying to describe. A lot of concepts is the same, but we want to add the flavor of high charges, high currents. Second thing is like relativistic gamma factor will be very close. and the speed of electrons very close to the speed of light. Okay, what I want to do next. So I'll come back to this table later on, but what you see here, basically the part what we call explosive electron emission. Explosive electron emission is nothing but field emission, except that we are providing too much electric field intensity, 100 kilovolt or above to 1 megavolt per centimeter. These high fields, what will cause the material that you use for your cathode to suffer from what we call explosion of these small micro points. If you go like smaller, if you have a microscope, you can take a look at the graphite or any metal, you're gonna see like small points, micro protrusions, and those points will, there is a lot of current will go through them because you have a high field, and they cause like explosion for them, and they form a plasma. Okay, now when you form a plasma, electrons are lighter, ions are heavier. So electrons will try to follow the equipotential lines to go to the anode or other different potentials that are around them, but ions will have very slow speed or spread velocity. So for this reason, high power microwave, we are talking about 100 nanoseconds, because you have longer pulse, other than we don't need it in real application. If we have a longer pulse, what's going to happen, this ion plasma will start migrate toward the anode, and they will cause gap closure and impedance collapse. So there is no more generation of RF. This is our goal, actually. Another thing about this explosive electron emission, you can have an environment has a medium vacuum. So you don't have to, have your tube to be cooked and sealed for vacuum, and you can't, and this is for, lower microwave tubes that you just, if something happened, you just like replace them, you can't like open them. It's going to be very challenging to seal the vacuum back. But for high power microwave, we will always gonna need, especially in the lab scale, we're always gonna open up the system, break the vacuum, do something, and then put it back. So basically, we are just using some O-rings and gasket, like just to seal vacuum, okay level of vacuum, 10 to the -4 or 5, and we are good to go to run next experiment. And if you are using other type of emissions, you need higher vacuum environment to have an efficient operation. For explosive emission, you can get away by having medium vacuum range.
Vacuum contamination problem we discussed in the morning.
Yeah.
It doesn't matter here.
It does affect the system for high rip rate. So, if you have very high rip rate pulses, now like the next pulse will suffer from this. But usually our rip rate, we're talking about 100 hertz to maybe 1 kilohertz is a lot. So the system has the time to go back to the level of the vacuum.
With low repetition rate, because of the discharge, material, right? The environment, the vacuum will be disturbed.
Yes. So then outgassing is going to happen. Yeah. Yes. The vacuum is going to be disturbed for a small fraction of time. So I'm not sure like what level. It's not going to be dropping like to 10 to the -3. It's going to be disturbed for sure. But I think the range is still okay to have a lower rip rate. If you have
discharge, like graphite material, will be in the environment.
Yes.
After you stop the pulses.
Yes.
Right? It will contaminate the environment. Doesn't cause any damage.
I mean, like for our scale, like single shot lab experience, we don't have any problems.
Long-term use.
Oh yeah, the lifetime of the cathode is really, if you take a look at the lifetime, is really not high. So for graphite, you have probably 100,000 shots, and then you need to replace it. And the reason is not only that, but also after a couple of shots, the cathode will be conditioned, will be smoothened. So you lose these micro points. In fact, every time you have a micro point, explosion happen in this microscopic level. Okay, just to don't think about as a bigger event. It's very microscopic event. And the next pulse, you will. So after this explosion happen, you generate a new micro protrusions, new micro points, but they're gonna be reduced after a couple of shots. I think you're right. It has some effect, but for low rip rate, from my understanding, is not a challenge.
What's the duty cycle of these pulses? If it's smaller than it can be
short pulses.
Yeah, it's not a problem. Then.
Yeah. There's like less than 100 nanosecond.
100 nanosecond.
Yeah,
that's it.
Yeah,
no problem.
No, yeah. So it's not gonna be, and the rip rate is not high. So there is like a higher, lower rip rate, and there is a burst mode. So they have pulses, and then you're gonna have charging state and pulses, but still like lower 1 kilohertz rip rate. So I will come back to this and explain more about the, why people they start thinking about having fiber, how the coating will affect the cathode or improve the life of the cathode and the performance of the tube. But I just want to show next is one of the lab experiments. So it's basically when I told you that our gun, not actually like a separate device, has electrodes. It's basically everything is combined under a very high magnetic field. So what you see here, this is the pulse power system, CNO6 terminal, the coaxial line, and the pulse between these two electrodes. This is the cathode, this is the anode. If you are electrical engineer, probably cathode and anode is the opposite way of thinking, but here the cathode is the more negative charged electrode. And once you have this, you have to have your cathode holder, and then this is the graphite, what we are talking about. Why we are using tubular and annular type of cathode? Because we want to generate higher current. So they found that if you have a solid cathode, your current is can reach kiloamps, but it's not that high. In this, if you have a knife edge cathode, you will emit very thin electron beam, and the current is high. So we put everything under solenoid coils, as you see here, and then we insert the slow wave structure, and now you have the system. This is like a simple way of describing it. You need to align everything. Alignment is very critical in our devices, because if you have a misalignment, you're going to excite other modes. Those waveguides have higher order modes usually. The reason why, because you want to have a bigger pipe to handle more power. I have suffering from
atomic figure in the slow structure.
the alignment.
Yeah.
The alignment before we insert the slow wave structure. Before, so we aligned with the vacuum diode.
If you have this alignment, for example, with the electric load,
Yeah.
then maybe we can have the backward wave oscillation.
Oh no, so okay, so this is backward wave oscillator, what you see here. But you're gonna, regardless of the physics of the device, backward, exciting backward or forward, this depends on how you design the source in terms of the cavity dimension, slow wave structure dimension.
I mean, if we have a TWT,
Yeah.
and we have any misalignment,
Yeah, you're gonna be
the electric support load.
Yeah, but
120-degree arrangement.
Okay.
A bit some little misalignment.
Yeah.
So can we have any oscillation or power hole in the passband?
Yeah, you're gonna have some oscillation, but you might reduce the efficiency of your device, because you start interacting with especially for linear devices. We're talking about TM0 mode, And remember, the first fundamental mode for circular waveguide is TE11. TE11 is always there. You are interacting with the higher order mode. So TE11 in real life doesn't have any axial component of electric field because transverse electric. But in slow wave structure, it's not actually TE11. It is a hybrid mode because you have corrugations. And now you have a small axial electric field component that can interact with the beam if they come at the maximum if you shift it. So that's why you need to have good alignment in order to make sure to reduce one. This field is not only you design it and you come up with the design and you go around experimenting. It has an art behind it. Sometimes like people like design and make efforts, and then when they go to the experimental world, nothing is generated. There is like a touch that you need to do at the end to make things like have an efficient interaction. So not on any slow wave structure will generate RF for you. You can do an effort, but then things will change. So this is an experiment. So I probably, let's see. I think I still have the time I can write on the tablet. So you have seen Child-Landmer law presented by Kashif and others. This basically, what you have seen is basically for relatively low currents. What I mean by low currents is tens of amp, maybe per centimeter square if you're talking about current density. But if you want to have higher currents and high energy electrons, you're talking about relativistic level. And the relativistic level, you need to have some correction to your equation that governs or relates the current with the voltage. The Child-Landmer law, they call it 3/2 law in physics. And this is basically very interesting to follow. So I'll switch to the tablet if I can. Do I have share from here? Yeah.
Sir, hello.
Yeah.
Sir, I have a question that is, may we use plasma cathode instead of any kind of material, plasma cathode based electron source? Like you use in backward wave oscillator, like positron like type system. Can I use?
So what do you mean by plasma cathode?
Plasma cathode based electron source. I mean, first plasma or initiate and low density plasma are initiate first, then high power pulse will excite in excited electrode, then electron will be come out from the anode, then it will be its electron source, plasma cathode based electron source.
Yeah, I have never done this, but probably it's possible.
Positron, yes, yes. Actually, positron in positron, this kind of electron source are used.
Okay, yeah. I mean, is this an electron accelerator or a microwave source?
Yes, it's a microwave source, and as it's not need a high vacuum level, so a small amount of gas are stay in this chamber. So as plasma are generated, so high current can be drawn in this system.
Mm. Okay, makes sense. Yeah, I never used it. We try to use cold cathode for simplicity because the devices are already complicated. So you don't want to add any plasma to as a source of electrons. But probably you will see a zoo of these devices. Most of them they end with the tron since they are electron devices. And people they try to mix physics of this and that and try to get like higher efficiency, improving some aspect of the operation, but it's very easy to, come up with a design and maybe even run simulation, but it's very hard to make it work in the real life. It's really challenging.
Yes, yes, but if yes, it have some obstacle, but if we can improve this, then I hope we can draw huge amount of electron beam current, because when system is total vacuum, then we can't draw a lot of current in vacuum system. So plasma assist microwave source, maybe it will be future high power microwave source.
Yeah, it could be. Yeah, I think it's always possible. And
Yes, actually I'm from Bangladesh. I have a small workstation in my home. I am trying to. I already developed in my home a Marx generator which produced 16 kV, and now I am applying it to build plasma cathode electron source. And if I successfully do that, I don't know, then I will be take attempt for positron related microwave source development. So okay, but
so is it
positron is working. Is under research work in the positron related microwave source. Many group are working, I hope.
okay? Yeah, we can chat afterward.
Yes.
Just you mentioned about the market generator. What's the level of voltage you are generating?
Actually, in my home, I'm 16 kilovolt. It's not too much. 16
Okay.
kilovolt.
Okay, once you reach hundreds of kilovolts, 500, 600 kilovolt, things will be like crazy.
Yes, yeah, it will be go relativistic electron source.
Yes.
It's when the pulse are excited, then electron are in relativistic mode.
Yes. Okay.
When yes.
Thank you. Thank you. Let's maybe chat afterward because we don't want to take time from others here.
Yeah.
Okay.
Thank you.
So this is the block diagram I showed you. Now, what I want to show you exactly that the power after the pulse power system here is basically pulsed. So we are talking about 100 nanosecond. A lot of events that can happen for longer pulse, you can avoid them by having shorter pulse. So it's kind of like engineering problem. Like, okay, there is other problems, but how to avoid them? You don't have, and as an engineer, you don't have to solve all the problems. If you can avoid problem, this is what you want to do. Make your life easier, make your system, working in real life, sell it, get some money. But for shorter pulse, and now we are talking about megavolt or MeVs and kiloamps of current, of not mega amps of current of your pulse. Now it's gigawatt of amp power. That's what you drive your high power microwave source. And now when I say high power microwave source, this is including the electron gun or your vacuum anode cathode setup, anode cathode gap. Okay, so this is one thing. Now don't confuse this. After the microwave source, what's gonna happen? You're gonna have a RF signal pulsed. Now you have high frequency, and this is what you are trying to radiate. If you want to change the mode, you can have a mode converter here, what I call a RF extraction. Okay, there's a lot to say about this, but I'm just trying to put you in a context that our cathode anode vacuum system is already combined with our high power microwave source. That way you don't have to have any additional electrode biasing with different voltages, and this is very expensive, very hard to do if not impossible, in this high voltages and high currents. Now, if you're talking about the this level of electrons, you have probably, you know, saw some of the modeling and some of these concepts related to single particle theory, or maybe statistical model. All of these, you need to understand them in a context that starting from lower voltage, lower current, Child-Landmer law, if you have two parallel plates, one of them is more negative than the other. So this is the electrode or the cathode, and the other one could be a plate, or could be, you know, a grid. But, you know, you don't want to have them, if you are talking about high currents, you don't want to have them close to each other. The arcing is gonna prevent you from having any good electron emission. Now, if you have your, now if the electric field like this way, then of course the electrons will come here, and then some of them, they're gonna hit this grid, and some of them, they're gonna fly here. And if there is nothing, they want to come back toward your ground here. But for our case, since we are integrating this with the microwave source, we force them to follow some magnetic field, static magnetic field, B. You can have any arrangement of that. Now, if you have this, now you are generating magnetic field lines. And I'm using black for the electrons, but I usually use red. Now, these electrons will continue. Maybe if you have the whole cathode anode gap in parallel, very uniform magnetic field, they're gonna go in one direction like you see here. Now, if you have this arrangement, if you have a high B field, now you have most of the electrons gonna have axial velocity, and the transverse velocity will be reduced, right? If your setup is right here, if your electrons are born here, your electrons will have a gyro motion, okay? Now, based on this, people like try to optimize one phenomena and reduce others to enhance or to design some source. If you have electrons here and the electrons start having gyro motion, this is the basic principle of gyrotron. If your electrons in the parallel magnetic field, now you have a beam, you can use it for linear devices, PWT, backward wave oscillator. You can change the voltage between these two electrodes, and maybe like I can write out here, cathode anode gap, and the voltage here maybe be 0 and this is 0, or maybe this is at anode at the ground and the cathode at the negative voltage. If you have a voltage here, imagine that you can increase the voltage, Do you think that the electrons will continue to be emitting from the electron? The answer is no. There is a limit, and this is what they call the space charge limiting current. Okay, and the space charge limiting current is following the Child-Landmer law. If you don't have a magnetic field in this case, that's the most of the electron gun for the thermonic emission. You are like having a force, Lorentz force is basically related only with the electric field, which is due to the pulse or the voltage between anode and cathode. And now we are talking about M. Let me maybe start a new line here. You have M dV dt equals minus. This is from the Lorentz force as the we described if you combine with the Newton's law, right? So F is nothing but And this is, you can use it as the mass acceleration or dv dt. So combining Lorentz force with the Newton's law, and if you have only electric field external from the pulse, you're gonna end up with having electrons emitting from the cathode to the anode here. And these electrons will suffer from Coulomb's force, right? And they're gonna push each other. And once they're gonna push each other, they start oscillating. What's the name of this frequency of oscillation in this case? Plasma frequency, right? So it's basically plasma frequency is a number of electrons that you can, each electron will feel, electron charge, the media around it to the half. So if you have this phenomena and you can enhance it somehow, maybe you can get up with a device that can generate frequency with the plasma frequency, RF signal with the plasma frequency. This is called breakator. Okay, if you enhance this phenomenon. Now imagine that you have your electrons will only experience external magnetic field, static magnetic field. So M dV dt. So you're gonna have this portion right here. So the electrons, what's gonna happen to electrons if they're gonna experience magnetic field from a static solenoid magnet or permanent magnet? These electrons will be having this gyro motion. So they're gonna have a gyro motion around these magnetic field lines. What's the name of the frequency of gyro motion in this case? Yeah, so this is the normal radius, and the frequency is cyclotron frequency, correct? So cyclotron frequency is gonna be the frequency that you're gonna see electrons moving with. And if you enhance this, this is basically the basic principle of gyrotron. You can enhance this somehow, and you can design it very well. You can have a source called gyrotron. Of course, the normal radius is the radius of this motion, can be given as where the velocity can be written as a vector as parallel component and perpendicular component, correct? So you, from the vector analysis, you remember how to write vectors in terms of their tangential and normal component, or parallel and vertical component. So since this is the gyro motion, you're going to have mostly transverse velocity and not the axial velocity maybe. Now, if you have your electron suffers from both static and magnetic field, static electric and magnetic field, now you're going to have both drifting in both direction basically, right? And this velocity called E cross B velocity, transverse velocity called, or maybe proportional, no, I'm not going to be writing it equal, called E cross B drift. So if you have the electron cloud or electron beam suffering from this transverse velocity, and the velocity of this is going to be perpendicular to both because this is cross product. And this is what you see in magnetron, basically. You have cathode and electrons will be drifting around, suffering from or under influence of this transverse velocity. Sometimes they write it as E over B as the magnitude. Now, if you take a look at M, is like if you are talking about non-relativistic electron cloud, M is just a rest mass, probably is enough. But if you have a relativistic level of electron movement, now you have to have a gamma relativistic factor involved, which is basically can be calculated. Can be calculated also from the applied voltage. And we usually write this, the equation I just showed you, Let me rewrite it here for you. 1 plus V in megavolt 0.511, right? This is, let's say this is the cathode gamma. Once the electron leaves the cathode and go to the bounded structure, will suffer from what they call voltage depression. So their gamma will be reduced by some delta gamma. But this is like so much complication that you don't want to worry about at the beginning of studying this field. You just want to assume your electron gamma is basically close to the cathode gamma. Where is the 511 comes from? Do you guys have an idea?
Mass energy,
Yes.
electron mass energy.
Yes. So this is why we call it 500 kV. This is what we call like relativistic level, because it comes from the reduced electron energy, so it's basically. Okay, so lower than that, things are a little bit easier, but closer to this level, things will get so tricky. Now, if you go back to Triad-Landmer law, either in parallel plate setup or any other geometry, it's basically electrostatic boundary value problem. You studied like in differential equation, boundary value problem, you have a differential equation, boundary conditions, or maybe initial conditions, and then you solve them. Probably in the math level class, you just do abstract math. You don't have much of sense what's going on, but it's basically here, it's the same idea. Some Laplace equation, and you have boundary conditions and initial conditions, you apply them to find relation between maybe current and voltage, or maybe relativistic factor, and so on and so forth. So like, this is basically a differential equation that you solve. You don't have to solve it, but I think at some point, if you are specialized in this field, you need to do it by hand just to have a feeling how things work, and and relate them your mathematical model with the real life and simulation. So for Triad-Landmer law, it's basically two parallel plates. Everything we do here, we assume the environment is vacuum, right? If we have non-vacuum or poor vacuum, your electrons is not going to be streaming. It's going to be colliding to the air molecule, and it's not going to help you to do anything with them. You can't extract energy. So parallel plate is the simplest task, but it's basically, if you solve it, you can go ahead and have your one of the plates like this, and the second one you can have curved. Imagine it is completely curved. What's the geometry now? Coaxial, right? Yeah, so coaxial gonna be. So you can use Cartesian rectangular coordinate to solve any system and any coordinate system, but it's gonna be difficult. You need to have some sort of symmetry to reduce your math and make sense out of what you are doing. I will show you this once we're talking about slow wave structures. So it's the same idea, coming from parallel plate and changing. Now, in this context, what I'm talking about vacuum diode, we are talking about these plates. One of them is cathode, one of them is anode. We are generating electron out of them. But when we go to the waveguide, when one of them is one plate, second plate, either is gonna guide the RF, or you wanna generate RF between these two somehow. Slow wave structure use in this case. So it's basically similar concept, except that what phenomena you are using, you can't separate them because we are trying to extract energy from electrons. So that's why I said at the beginning, we are combining the diode with the slow wave structure to have the best performance, and we call this interaction region. Okay. Any question about this? These basic concepts?
I have a question.
Yeah, go ahead.
Sorry. You mentioned that if you apply something on the electron will be relativistic, And you also mentioned that the relative electrons will be as mega electrons.
Yes, right.
Does work. So because we are applying kilovolt and getting megavolt electron. I didn't get it actually.
Okay, so why we're now, once we apply voltage, we call it kilovolt. Once we have electrons flying, we call them MeV. This is your question, right?
Yeah, exactly.
Okay, so in this field, I think in even in accelerator physics, this is basically, they think about voltage as energy and current as power. Is not like precise, but it helps you to understand a lot of concepts. Now, once you apply voltage between two electrodes, and this energy, once they go to a state where is electrons flying in vacuum, this is convective convection current, right? Not conductive. There's no conductor anymore. Now you are changing the physics basically, and your energy should have to move from one stage to the next stage, right? Somehow. How can you describe this energy? Yeah, it's not gonna be, current and voltage anymore. I mean, it's current and voltage, but it's not in the conductive way. It's basically streaming in vacuum. So now it's easier to describe them as, energy of electrons than the voltage between the electron beam and the wall. You could use that. And actually, when you solve the boundary value problem, you actually starting from that you are considering voltage difference between, or potential difference between the electron and the wall, which is the anode. But I mean, like, this is probably like comes back to the basic concepts. You can't separate things like energy, power, voltage, current. Everything is the same as a phenomena. They don't know if we call them voltage and current. It's for us to understand, right? So these are terminologies. Yeah, is that helps a little bit?
Yeah, it helps, but for example, let's think about an X-ray tube. So if we apply 100 kilovolts to an X-ray tube, the output as photon,
Electron will emit.
Photons, the high end of the photons will be at 100 kilovolts. So I will investigate more because I need to fully understand.
Yeah, you need to absorb it.
And why mega electron?
Okay. So you're aware of this, like you can write it in terms of joules, but this is very small in terms of joules, right? It's just changing to electron volt because we're talking about. Okay. Anyways, so you can maybe discuss even with others. Like, I think everyone have a good background, so they can help if my answer is not good enough. So this is very, very good kind of description of what's going on in the vacuum diode. What I want to also add, okay, is that so for this parallel plate, I think you guys have seen it, but I just want to rewrite it here in the relativistic level, is that the Child-Landmer law, which is the relation between the current, space charge limiting current, is 3/2, probably, if we are talking non-relativistic level. And this is going to give you kiloamps per centimeter squared. Now, if you move to relativistic level, of course, you can write it that in 1D or more is going to be a slightly different value. And I want to just write it here just for your reference. These are approximations 1D model. And you notice that you will have to include the relativistic effect if you are passing 0.511 kV. And this is what you see here. And this is the space charge limiting current for parallel plate. And if you are having a different geometry, let's say that you have a coaxial geometry. Now in 1D, now the coordinate system is going to be different. And if you solve the electrostatic boundary value problem, you're going to have something very similar, which is basically gonna involve you the radius of the these coaxials RA and RB is anode and cathode. You can have the anode outer cylinder or the cathode outer cylinder is not a problem. Now, this is 1D model. Now, if you have I think I need to move to because it's going to be very lengthy or very complicated drawing. Let's move back to the PowerPoints. If you have two cylinders, but yeah, PowerPoint. Two cylinders, and you want to inject your okay. I'll come back to this, but if you have two cylinders here, and you don't want to have the inner one or the outer one is the cathode. You want to generate a ring of electrons and send it in the interaction region, and this way will require you to have maybe more careful considerations about your ring. Is it going to be like sending the ring in the interaction region in some axial speed, or is it going to be like going in helical direction? And this is going to be contributing to your RF generation. So going back to here, since we have a lot of current, we are generating a lot of current, and this is now you remember this is the relativistic factor. What is going to happen to the electron beam is going to happen, you're going to cause pinching to it. So it's going to have some squeeze state for the electron. And this is very, very bad kind of instability to your electron beam. Also, some, rotational behavior, as I was describing. Now, this rotation is going to be cyclotron frequency for the whole beam. That's why we're using kind of like a big omega for whole beam is going to be suffering from the cyclotron frequency. And this cyclotron frequency, if you are designing backward wave oscillator or other devices other than gyrotron, this is negative thing that you need to reduce. If you are using gyrotron, you need to enhance this behavior. So as I was describing for this case, if you are sending the electrons from a region where the magnetic field lines are bending, this is gonna enhance the cyclotron frequency of the electrons. For linear devices, the cathode, as I showed you in the lab pictures, the cathode is here, and the electrons will be emitting, and if you want to solve your Laplace equations and differential equations, basically you're going to divide the region into a couple of regions, region 1, region 2, and you need to assume the electron has a very thin delta thickness that does not going to contribute to the solution. Otherwise it's going to complicate your analysis. Now, if you inject the current here, and the current is high enough that reaches space charge limiting current or exceeded, you're gonna have this behavior here. And if you exceed this, your beam current greater than this threshold, you're actually doing a virtual cathode behavior. And this is basically plasma frequency oscillations that I was describing. This comparison between the annular and the solid beam, and you can see for annular beam, you have much higher current you can get out of the same material, graphite material. So kiloamps here in this level, and this is with the same voltage, applied voltage. Let's assume that you have 1 megavolt applied between cathode and anode. You can generate maybe 5 to 10 kiloamps if you have this ratio between the wall and the beam. But if you're having annular beam, you're talking about 40 kiloamps. It's very, very high current. It's not, you don't want to have any electrodes near to it. They're going to start arcing. It's really a challenging task. That's why we don't design electron gun in a way that people at lower currents do with the electrodes, different voltages, of course. And also the pulse width is contributing to. I will talk about this, the magnetic field between the anode and cathode and this coaxial or azimuthal symmetric geometry like magnetron. Is there a question? So this is gonna come back when I talk about relativistic magnetron. So I'm not gonna describe this in more depth, but the bottom line that I was talking about, all the geometries can be approximated as a parallel plate if you just open this in some way, and then you have them as a parallel plate. This is the cathode, anode, and then you can simplify your task to understand much about the physics of the device, either vacuum diode or maybe microwave source. We call these devices as magnetically insulated vacuum diode because we are always going to have a high magnetic field to insulate the electrons from going back to the anode, and then we can use much of the energy. Now, if you send this high current beam or maybe cloud inside a bounded structure, of course, the beam does not have very thin thickness. It has a thickness, right? It's impossible to have, even though we are using sharp knife edge cathode, but still has a thickness, probably like maybe have a millimeter thickness. Now these electrons will start having Coulomb's force. They're gonna push each other, right? Similar charge. And then we can approximate them as two groups, what we call the fast group, the one like having a little bit faster velocity, and this is going to be the plasma frequency of the beam with the relativistic factor. We're going to have fast space charge wave and slow space charge wave. And usually with the high power microwave sources, we are interacting, the electromagnetic wave interacting with the slow space charge wave, not the fast space charge wave. And this is very, very critical because people they think the electron, at least they simplify it as the monoenergetic electron, has one energy, one velocity, and they design their source. And when they go to experimental world, they generate lower frequency because they are not interacting with the average velocity that they think is the velocity is going to be shifted by this term. It's like Doppler shift, basically, with the plasma frequency. This is very important concept if you want to design a source or maybe analyze a source. So again, maybe like a little bit about this, maybe to continue. So once you have the slow space charge wave interacting with the electromagnetic wave, you will start having, you know, you need to have to consider the electron current or the electron streaming in the same direction as the electric field, and this depends on the geometry, right? If you have a linear device, now the electron is streaming in the axial direction. But if you have a circular device, electrons streaming in E cross B drift this way. So that's why the interaction with different modes. At the beginning, we talked about electromagnetic modes are really critical in this field in high vacuum microwave devices, because if you are having a linear device, you need to have some strong electric field in the same direction of the electron streaming to satisfy Poynting theorem, right? And then you're going to have an interaction of the electromagnetic wave. Other than the resonance, what we call Cherenkov resonance in our context, at least the devices we're going to discuss maybe tomorrow and after tomorrow, magnetron and backward wave oscillator, those are kind of a Cherenkov devices. So basically, the electric field in the structure will perturb the electron streaming, then modulate it, then bunch it, and then decelerate it because they took the energy out of it, right? And if you have a smooth wall, if you don't have any sort of slow wave structure, you know, there is no interaction. Nothing is going to happen. The electrons will pass ideally. In lab level experiment, you might generate some RF, but it's very weak, very inefficient interaction. And this is from the other day I just showed you before. After bunching, this is what happened basically. You know, bunching happening, and then they start like radiating RF. This is an electron, free electron laser, but this principle is correct for most of the devices. Yeah.
What about the phase of the electromagnetic radiations coming out of this type of experiment?
Yeah.
Are they phase locked?
Oh, so it's really like a random phase. Pulse to pulse is going to be like, yeah, it's very random. If you are talking about oscillators, of course. If you talk about amplifier, we'll be locking with the seed signal. So you can, if you have a solid state input injector, you're going to control the phase at in some degree. But for oscillators, free running oscillators. Yeah. The thing is, the application is gonna help you because you know the application that you know with no if you go to communication, maybe other fields, you need very precise phase. But if you talk about defense applications, basically okay to use like some sort of free running oscillators. So other than for the cathode, other than the lifetime of the cathode, there is other problems. We talked about the plasma formation on the cathode, and this plasma start migrating toward the anode. And because of the electrons hits the walls, the anode, some plasma will form and then migrate back to interaction region and then maybe close your gap. One way of reducing the speed or like the velocity of this plasma moving, usually they approximate as a couple of micrometer per second. I think the velocity of the plasma, if I'm not wrong. Yeah, and if you have some coating on your graphite maybe, and this is can help you to have a slower plasma expansion, and that's why they use some sort of coating around it. And also, if you have your graphite emitting after a couple of pulses, you'll start suffering from non-uniform emission points. So your beam is not uniform. It has some hot spots, some less, dense spots, and this is gonna reduce the microwave source efficiency. So they use fiber to improve this. So these are some variations, and this coating helped to improve the pulse shortening, basically, because they reduce the speed or the expansion velocity of the plasma. And this is an experiment, I think, from Air Force Lab, Dan Schiffler. So they improved the pulse by maybe the double of the pulse. But this is for longer pulse. You see, their pulse, for their facility, Orion facility, is very long pulse. For real life, our pulse is around like 100 nanoseconds. So we can get away. We don't need to do this advanced technology and add more cost to our device. Very fast pulses.
This cesium iodide coating. Am I right? It's cesium.
Yeah. Yes. Yeah.
So what is maybe the thickness? Maybe I missed it. Or it is.
It's coating. Yeah. I mean, I don't know exactly the thickness, but it's coating. So probably it's very thin layer around the cathode.
Goes away with the every shot. I mean, do you have a mechanism to replenish?
I mean, the lifetime of those is not. They claim it's similar to have a graphite right here. Yeah, with the high rep rate too. So it doesn't seem to need much of repair. Maybe at the end of this, you just need a new cathode with the coating.
And when you say carbon fiber, is it graphite, graphene,
Graphite?
or the nanotubes maybe? Well, fibers are of many types.
Yeah.
What type of allotrope are they?
I have no idea. This is, in this field, they just use the common material. So they don't have a very strict about purity and other properties. But I never used these. We just use graphite all the time. And probably we have cathode that we are running since 2015 for 10 years. Because we're just like in a lab, scale. So we don't have higher rate. Yeah. I think I passed the time, right? Yeah, I think I'm done. I can talk about. There's a lot to talk about. So, but I'm just trying to, fill 1 hour. Yeah.
Hour in 5 minutes.
Yeah.
And then we can.
Let's see. Maybe they have questions. Online people or in class. Do you guys have any questions?
Okay. Is there any question?
No questions. I think either everything. Yeah, go ahead.
Sir, pulse shortening is when plasma is conductive, so then it stop the pulse formation. Is it right when plasma is formed in cathode?
Yes, when the plasma forms on the cathode and expand and close the anode cathode gap.
Yes.
This is where
Short circuit.
Yeah, correct.
Yes, it stop this oscillation. Okay,
Yes.
sir. Now, if we build so high power magnetic field around the cathode, then plasma ions are trapped around the cathode. So the ions are not easily moved to the anode. So we can improve the shortening time. Is it possible?
I don't think I got your question. Can you just rephrase it?
Okay. Plasma can magnetic field can trap plasma.
Trap plasma.
Yes, trapping.
Right.
Okay. If we build so high power magnetic field around the cathode area, then when plasma are formed, it cannot escape. It will be trapped. This region, like magnetic mirror.
Okay, so you're trying to have a magnetic field at the cathode is different than the magnetic field in the interaction region. So you're gonna have different, stronger magnetic field on the cathode. Is that correct?
Yes. Then it will create a magnetic mirror.
But having this, you're gonna just think about the plasma. What's gonna happen to the electron? You're gonna have what they call electron compression or decompression. Your electron
Yeah.
not gonna
Yeah.
go back in a straight line.
Mhm.
Yeah, so they're gonna away from the slower structure. So yeah, you're gonna lose the electrons electromagnetic wave interaction.
Yes. But if we create a E cross drift force, then I hope ion are move backward and electron will forward. Then I hope we can increase our pulse time. Yeah, but in the meantime, I can't express shortly. But by magnetic field and E cos B drift force, we can increase this shortening time. I hope.
Okay.
Yes.
Yeah, if you can try it and share the results, will be interesting. Yeah.
Actually, I am working for my passion. So I am thinking about that. I have enthusiasm in plasma physics, hyper micro source development. So I am thinking personally, but I have no. Actually, I complete my masters of philosophy physics in plasma. Plasma is my major. So I'm trying, but I need facility to prove this type of work. So I just express my ideas short, what I am thinking before on power shortening. Yes.
Good. Thank you. Yeah, everything like there is infinite number of possibilities. But every experiment people like do it. Every experiment is expensive. So
Yes.
thank you so much. Thank you everyone, and enjoy the rest of the talks. Yeah, question
In Zoom.
in Zoom.
Right.
El kaldırma vardı da.
In the messages in the.
And, is there anyone else to ask
Any other question?
from Zoom? Okay. Thank you very much.
Thank you.
For the very deeply understanding. And
Thank you.
we will continue on 3:25 p.m. again. See you.